Hello, hello, hello. In this worked example, we're going to be talking about rocket to Mars. In particular, the SpaceX company's proposed system, the Interplanetary Transport System, for sending humans to Mars. They have incredibly ambitious plans to colonize Mars, sending rockets which can take 100 people at a time to Mars. Uh, it's judging, this is called the Starship. That's the name of the booster engine. It's a very ambitious project. It was initially referred to as the BFR. And judging from the size and demands on this rocket, you can probably guess what BFR stands for. We're going to try to think about the physics of how such a big vehicle operates and what it takes to get to Mars, and we're going to analyze the situation in terms of our two rocket equations that we've previously discussed. So let's dig in. Okay, so let's watch a little bit of the promotional video that SpaceX put together. This is now about 5 years old. This was their vision. And at the end of this worked example, we'll have a reality check and see how far they've actually gotten, which is actually still pretty impressive, but still a long way off from this vision, but they've made a lot of progress. So let's look. So there's the crew, and this gives you a sense of scale. It's a pretty big rocket. A lot of engines. We need a lot of thrust. Launching from the same place that the Apollo moon flights took off from, at Cape Canaveral, Florida. We have ignition, and we have liftoff. And let's pause for a second there. Let's look at the numbers. 1.25 times 10 to the fifth kilonewtons of thrust. That's 1.27 or 1.28 times 10 to the eighth newtons of thrust. So that's the effective force that's acting on the rocket. Remember, this term here, that what we call the thrust, is just the product of the rate at which mass is being expelled from the rocket and times the exhaust velocity of the fuel, which is in this case proposed to be a liquid methane carried on board that's burned as the fuel source. And looking at that number from the thrust, you'd guess that the rocket at liftoff has an enormous weight, because you need more thrust than the weight of the rocket to have it lift off. And that corresponds to a mass of something like 1.3 times 10 to the seventh kilograms. So that's more than 10 million kilograms of of mass. So it is indeed a very big rocket at the time of liftoff. So let's watch a little bit more of the promotional video here. Okay, let's pause here, because here's another interesting way of connecting to some of the physics that we've been talking about. Part of the challenge to get up into orbit and then eventually to get enough speed to escape Earth's to achieve escape velocity and make it to Mars, you got to be going pretty fast. Eventually you're going to get up to speeds of something like 100,000 kilometers per hour. But early in the flight, you're still going pretty fast, 3,500 kilometers per hour. That's more than 2,000 miles an hour. And you're still in the Earth's atmosphere. It's getting thinner, less dense, But when you think about drag forces, remember the drag force is proportional to the square of the velocity. So if you're moving more than 2,000 miles an hour and you're still in the Earth's atmosphere and you've got a pretty big um, surface area here, there are enormous drag forces that are pushing on the nose of the rocket. And that's pretty much what they're talking about here. That's a real engineering challenge to be able to withstand all those forces. Okay, so let's keep going here. Okay, we've made it to orbit. Now here comes something pretty cool. We're gonna drop one stage. And why do we do that? Let's talk about that for a second. Remember, um, the final velocity that you obtain depends on making the final mass of the rocket small compared to the initial mass. It also depends on the exhaust velocity, but there's a real premium paid for getting for not taking a lot of mass with you at the end. And so you want to get rid of now that you've spent all the fuel in this stage. You want to get rid of it. There's no because the casing itself has a lot of mass, and that is literally just dead weight. You certainly don't want to take that to Mars. So that's going to go back to Earth. And now here comes something really cool, and this is more of an engineering economics problem. Let's watch what comes next. It used to be they would throw these things away. They would just burn up in the atmosphere on the way back down. But watch what happens here. This is part of what is going to make, allegedly make traveling to Mars economically feasible. You don't have to throw away things. If you're going to colonize Mars, you're going to send a lot of rockets, and you're going to throw them away. So it's important to be able to land back on the launch pad. And now, here's another cool thing. You still need more fuel. You still have a lot of more speed, and you to make it all the way to Mars. And we're not quite there when we're in Earth orbit. So you need some more fuel. So now we're refueling in space, in orbit. Now you want to go pretty fast, not just to sort of get this escape velocity, but you don't want the trip to take too long. So we want to get to Mars pretty quickly. It's going to take 7 months as it is. And even 7 months, you're going to need power along the way. So you don't want to carry a lot of fuel for power. So you use solar power to run operations while during that 7-month period. And we're cruising. And I think they're going to give the speed here coming up. They've achieved a cruising speed, as I said, I think it's something like 100,000 kilometers per hour. Yeah, exactly. There it is, the interplanetary coast. Sir Isaac Newton is in the driver's seat right now. Just gravity is the only force acting on this rocket. There's the red planet. Okay, so that's the hype. Let's see how far along they've gotten. Let's look at some real video. This was today. I'm recording this on March the 16th. This is video that was shot on March the 3rd, 2021, coming up. Okay, so we're going to show a test launch. This is not the BFR by any means, but it's got a lot of the technology. It's got a small number of the engines that are ultimately going to be on board. And this test flight is designed just to send the thing up at a relatively slow speed, just have enough thrust to basically barely be greater than the weight of the rocket, and it's going to get up to an altitude of 10 kilometers or so. It's never going to be going very fast, but they want to be able to demonstrate this ability to land back on the launch pad, and they've gotten pretty close. They've had a couple of test flights where they basically looked like it was going good, and then they basically, as just when at the end when they touched down, the whole thing exploded. So those are pretty spectacular. But let's watch this portions of this test flight. So we'll start with the liftoff, which is coming up at well, we're going to count down. Not much to say here other than suspense and waiting for liftoff.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. We have liftoff. All teams, triage alerts, please. FC2, please prepare for section 35. OSC, FC1, LVN.
T plus 30 seconds, Starship 10 has liftoff. It's headed to 10 kilometers on its test flight from Boca Chica in Cameron County, Texas.
There's a pretty shot. Usually rockets are going so fast at this point that you can't fly along with them, but it's pretty spectacular.
Raptor engine.
Okay, so now they're basically, looks like they're just hovering. But now they're going to let gravity pull it back down to Earth a little bit. But remember, you don't want to go too fast because you want to land softly on the launch pad. So now they're using a little bit of aerodynamics. This thing has some wings on it, so it's a little bit like an airplane at this point.
T plus 4 minutes and 40 seconds. Starship has transitioned. It's flipped to the horizontal mode, beginning the descent back to the landing zone. Coming up on 5 minutes, 45 seconds. We're down below 2 kilometers. We're preparing to light 3 Raptor engines to begin the flip sequence. It'll culminate with landing on the landing pad in Boca Chica.
There we go. Pretty cool. And we'll just finish up by watching a little victory lap of the announcer summing up the flight.
Third time's a charm, as the saying goes. We've had a successful soft touchdown on the landing pad. That's capping a beautiful test flight of Starship 10. As a reminder, the key point of today's test flight was to gather the data on controlling the vehicle while re-entering, and we were successful in doing so. We had a nominal ascent. We had the maneuver to place Starship horizontal when we reached 10 kilometers, right on time. And then during the subsonic entry, it appears we had good control of the vehicle using the front and aft flaps. And as we approached the landing pad, we successfully lit the 3 Raptor engines to perform that flip maneuver. And then we shut down 2 of them and landed on the single engine as planned. A beautiful soft landing of Starship on the landing pad at Boca Chica. Also, a congratulations to the Starship team in Texas. They've steadily increased the test launch cadence over the course of the program and have delivered some of the most exciting test flights many of us have seen in a long time. The Texas team has several more suborbital test vehicles in build, with number 11 ready to roll out to the pad in the very near future. It's an inspiring time for the future of human spaceflight. Thanks for joining us today, and we hope you'll join us for the next test flight of Starship 11.
Okay, so that's the reality, and again, it's not it doesn't quite live up to the hype of the promotional video, but there's a lot of great engineering that has been achieved so far, and it's anybody's guess whether they'll really colonize Mars anytime in the next decade or two. But it's pretty interesting to be an observer to all this. So that's it for this worked example. Hope to see you again soon. Bye bye.